Okay. So we should be recording. Just want to double check. Yes. Okay. So I'm going over complement of an event. So this is actually something that people kind of get confused with when you have words of less than, greater than, and that kind of thing. So I'm going to sort of focus on those type of complements and show how you can use the complement to find, certain values. So just to start out with vocabulary for probability, an experiment is anything for which the result is uncertain. Outcomes are the possible results. When you have the set of all possible outcomes, it's called a sample space. A subset of a sample space is an event. And if we have an event E that has N of E, not equally likely outcomes, N standing for the number of outcomes, and its sample space N or sample space S has N of S equally likely outcomes, so the number of possible outcomes in the sample space, then the probability of event E is, and we use P to represent probability of E, is N of E over N of S. Essentially, you're just taking the number of ways the event can occur divided by the total possibilities in that sample space, and that's your probability. So I will be using this notation, the P of E notation, but instead of E, I put in a description of what the actual event is so that it actually kind of makes sense. So the complement of an event. So if you have event A, the complement are all the outcomes that are not that event. So we write that as A prime. And prime is what we call that little apostrophe there. So that's read as prime. So you have A occurring, and then you have everything that's not A occurring, and that's the complement. So there's no overlap between these. So they are mutually exclusive. And because of that, you can add their probabilities. And when you add them up, you get 1 because it's either happening or it's not happening. So the total probabilities is 1 because that's 100%. And so if you want to know the probability of the complement, you do 1 minus the probability of the actual event. So we're going to be doing 1 minus a lot in figuring out the complement of an event here. So I've got 3 different examples to demonstrate using this concept of the complement. So the first one here, we want to find the probability for the experiment of tossing a coin 3 times. So if you're tossing a coin 3 times, order in this case matters. So, you can get a head or a tail. You might get a head first or a tail first. Order matters. So we're going to keep that in mind here, that the order matters. And so we want to find the probability of getting at least 1 head, and then the probability of getting at least 2 heads. So we're going to start by writing down the sample space for this. If we're doing something more than once, I like to write down the sample space, especially if it's a pretty small sample space, so that I have an idea of what I'm actually looking at and all the probabilities. So we could have 0 heads, and that would be if you get all tails. We could get 1 head, and we could get the head first, or we could have it second, or we could have it third. So there are 3 ways to get 1 head if we're tossing a coin 3 times. And then we can have 2 heads. And there's also 3 ways to get 2 heads. And then we have 3 heads, which is just head, head, head. So trying to fill in all the possibilities here. Should have made this slightly bigger. So that's our sample space. And I'm focusing on the number of possible heads we can get because that's what our events are. We're looking at the probability of getting at least 1 head or the probability of getting at least 2 heads. So I'm focused on the heads. And so I split up my sample space based off of, we can get 0, 1, 2, or 3 in those 3 tosses. So we can do these by literally counting, the probability of getting at least 1 head. We can count how many are 1 head, 2 head, and 3 head and add those up. But it's actually easier to do it by finding the complement. So the probability of the number of heads being greater than or equal to 1. So I'm going to use H for the number of heads. And if you have at least 1 head, then it's going to be greater than or equal to 1. So at least includes the one that you have. The complement is 1 minus the probability of 0 heads. So that would be the opposite. So if we have at least 1 head, we're including 1, 2, and 3 heads. So the complement, the opposite of it, would be 0. So it's a whole lot easier to do the probability by looking at how many, ways there is to get 0 heads, and then doing 1 minus that, than to count up all the possibilities for all the other ones. So 1 minus the probability of 0 heads, there's only one way to get 0 heads. And if you count all the possibilities you have here, there are 8 possibilities. So I'm going to just put this on top. For each toss, we have 2 choices. So you have basically a 50-50 chance of getting either a head or a tail. And so there's 3 of those. So the total number in our sample space is basically going to be 8, 1 out of 8, for one of our choices. So our sample space is actually going to be 8. So we've got 2 choices. I should write that this way, 2 choices, 3 different ways. So there's 8 possibilities. So there's only one way to get 0 heads. So that's going to be 1 over 8. So our complement is 1 minus 1/8. And so this gives us 1/7. So the probability of, not 1/7, 7 over 8. I don't know why I did 1/7. That is definitely not mathematically right. So the probability of getting at least 1 head is going to be 7 over 8. You can convert that to a percentage if you want. You don't have to. We can leave it as a fraction here. But that would be the same. It's the same thing as if you literally counted up the number of 1 head, 2 head, and 3 heads there, and you've got 3 plus 3 plus 1, and that gives you 7. But as long as you understand how the complement works, okay, there's only 1 that doesn't include heads, and that's all tails. So that's 1 out of the total, the 8 that you have there, and that gives us 7 over 8. Now we can do the same sort of thing to find the probability of getting at least 2 heads. So the probability that the number of heads is greater than or equal to 2 would be 1 minus the probability that the number of heads is less than or equal to 1. So you're thinking up, you're splitting up your thing, and you're finding the opposite. So this one, it's about the same amount of work to count up how many are greater than or equal to 2 versus how many are less than or equal to 1. It's the same amount of work, but I'm just showing you how you can use the complement here, especially when you have these greater than and less than things. So when you've got at least, then the complement would be the opposite at most, essentially, for the other number, where that cutoff is. So we can't include 2, we already did. So we're leaving it at 1. So the probability of the number of heads being less than or equal to 1, that would be 0 heads or 1 head. And so you can see there are 4 choices there, because we have 1 choice for 0 and then 3 choices for 1 head. So that's 4 total. So that's going to be 1 minus 4 over 8. And so that would result in 4 over 8, which is just 1/2. So I'm doing these with a complement. You don't have to use the complement in these cases, but sometimes it's easier to do the complement than to actually count up all the possibilities that you have. Are there any questions on this example? Okay. Oops, dropped my stylus. All right, so this next one. Find the probability for the experiment of drawing a card at random from a standard deck of 52. So this one, I'm not going to write down the sample space because we're not doing multiple pulls. We're just pulling once. So I don't really need to write down how, all of my possibilities, as long as you understand how a deck of cards works. So we have a deck of 52. So the number of values in our sample space is 52, because there's 52 cards to pull from. So we want to find the probability that we get a card that is not a face card, and then the probability that the card is 9 or lower. And in this case, we're considering aces as low, so they're not going to be part of the face card. Sometimes, depending on how you interpret it, aces are considered face cards, different games, but we're not including aces in that. So we're only looking for face cards, which are Jack, Queen, and King. And then we're going to consider aces as basically 1. So when you see something that says the card is not a face card, whenever you see the word not, that basically tells you you're kind of going to find a complement. You don't have to do it this way, but it lends itself to using the complement. So the probability that it is not a face card is 1 minus the probability that it is a face card. And there are far fewer face cards than there are other cards, so it's easier to do it using the complement because there's fewer cards that you have to deal with, just smaller numbers. So we've got 3 different face cards, Jack, Queen, and King, and there's 4 suits. So that gives us 12 face cards total. So the probability that you can get a face card is 12 out of 52. So I just use my calculator and, whoops, help if I cleared it first. So that gives us 40 out of 52 that are not face cards. And then I just use my calculator to reduce the fraction for me. You can reduce it by hand, but that reduces to 10 over 13. So the probability that we get a card that is not a face card is 10 over 13. The next event that we have here is that the card is a 9 or lower. So if we do this with a complement, so the probability that the card, and I'm going to just use C to represent card, is less than or equal to 9. So it's 9 or lower. This would be equal to 1 minus the probability that it is greater than 9. So this would be including 10s, jacks, queens, kings. So I could also write that as 1 minus the probability the card is greater or equal to 10. And then instead of greater than 9. But I just want to show you that you can use, if you're going to use the same number in your complement, then one has to be a greater than, one's a less than or equal to, or vice versa. So that way you're not having overlap there. So we think about what we've got here. We've got the 3 face cards, but now we're also including the 10. So you've got 10, Jack, Queen, King. That's 4 different cards that are greater than 9. And then there's 4 suits. So that's giving us 16 total. So this is 1 minus 16 over 52. So again, smaller numbers than if you were to actually count how many cards are 9 and lower. And it's not hard to do. I'm just showing you, that you can do it this way as well. So 52 minus 16, that gives us 36. So they're 36 over 52, which then when you reduce gives us 9 over 13. So the alternate way to do these card ones is that instead of looking at the whole deck of 52, is to look at only a single suit. Because if you notice that because there's 4 suits and they're identical with the number of face cards versus other numbered cards, you can look at it out of a suit, which is 13 cards, and find, so we've got 3 face cards. So that means there's 10 that are not face. And so that's how you get 10 out of 13. And then you can do the same thing for there are 9 cards. If it's 9 or lower, 9 out of 13. So this works that you can do it out of 13 instead of 52 if you're just basically picking a single card. If you're trying to pick cards of different suits, like if you're picking 2 cards and you're looking for maybe a diamond and a heart, or a diamond and a face card, and you're doing more complicated combinations, you can't just say, okay, it's going to be out of 13. You would have to use the full 52 there. But depending on how it's worded, if there's overlap, if it's asking for face card and then it's asking for a different suit, there's some overlap there. But you can look at a single suit because as far as the cards go in a probability, it will always reduce because there's 4 of every kind, so it'll always reduce by 4. So are there questions on this example? Okay, so this is a quick live tonight because compliments are not too bad. It's just trying to, figure it out. So this is my last one. We want to find the probability for the experiment of tossing a 6-sided die twice. And so this is another one where I write the sample space because we're asking for the sum. The event is the sum. And so I need to actually visualize, okay, what do these add up to? Because I just, I don't have those memorized, but also because you're doing something twice. And so it kind of helps to see all the number of possibilities. And we are including that you can get a 2 and then a 1 and then a 1 and a 2. So we're allowing that the order matters here. So we're going to start by just writing down the sample space. And I'm just going to start by, let's say you roll a 1 and then a 1 again, and then a 1 and a 2. And so I'm just going to put them next to each other. I know it's looking like 11, 12, and so on. But this is, the fewer things that I have to write here, I have to write a comma. As long as I understand what's going on here, I'm just basically writing the 2 possibilities that you can roll. And then you can start with a 2 and then roll 1 and then a 2. And you can see the pattern here. And then I can roll a 3 first, and then I can go through all the possibilities for rolling a 3. And then the next die. And then a 4. If you do enough probability problems, it's almost worth just having this written down in one spot to reference so you don't have to write it down every time, because doing the sum of 2 die is a very common problem. Actually, one of them's on the self-assessment, is about adding 2 die together. So those are just the combination of rolling 2 die. So the sum is at least 8. So we can add up all the ones that are 8 or larger, or because I'm doing this with complements, we're going to do the opposite. So the probability that the sum, and I'm going to just use S for the sum, is greater than or equal to 8 would be 1 minus the probability that it is less than or equal to 7. So we can add up all the ones that add up to 7 and then use that probability and do 1 minus that. So I'm going to just highlight all the ones that add up to 7 or below 7. And you'll see that there's actually a pattern here. So in the first column, anything 1 plus whatever the numbers, those all add up to 7 or lower. Then we've got that adds up to 3, 4, 5, 6, 7, 4, 5, 6, 7. And you can see that there's a pattern here. So it's really nice. It's half of them. You can see right there that half of them add up to 7 or lower, or they add up to some sum that's less than or equal to 7. So our total sample space here, we've got, and when I write it this way, I've got 6 rows, 6 columns. So our sample space is 36. And so you can go and you can count all these up, but it's going to be half, which should be about half. Let me make sure that I've added these up correctly. 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21. Okay, that's not half. So it looks like half in the way that I drew my picture, but it's not half. So there are actually 21 there. So 21 out of 36 here add up to, you know, they're going to be add up to a number less than 7 or equal to 7. So less than or equal to 7. So we just need to do 1 minus that. And that gives us 15 left over. And when you reduce that, that comes to 5 out of 12. So the probability that the sum is at least 8 is 5 over 12. And we did this by doing the complement, which is 1 minus the probability the sum is less than or equal to 7. But you could have instead just literally highlighted all of the ones that are at least 8 or higher, and then counted those up. So you can do it either way. Now, the second event here is that the sum is less than 11. And this is one where I would definitely use the complement. So if you know that you're going to have to be adding up a whole lot of things and that the complement is like adding up only 1 or 2 things, it's definitely worth it to do it by the complement. The previous one that I just here with the at least 8 is probably about the same amount of work either way. But if we want to know that the probability that the sum is less than 11, so we're not including 11, then the complement would be 1 minus the probability that the sum is greater than or equal 11. And that would only be equal to 11 or equal to 12. Those are the only possible sums we can get from tossing 2 die. So I'm going to use a different color here for my highlighter. And so we look at, we've got 6 and 6, which gives you 12. And then 6 plus 5 is 11, and 5 plus 6 is, maybe I shouldn't use green. That blended in very badly. And I accidentally erased my 6 here. Let's do, I have an orange. Maybe that'll work better. Okay, that's a little better. So you can either add up to 11 or add up to 12, and there's only 3 combinations that do that in our sample space. So this is one where it's worth doing the complement because you're adding a lot fewer things together. So that's 1 minus 3 over 36, because there's only 3 of them that are greater than or equal to 11. And so that gives us 33 over 36. And then that reduces to 11 over 12. And so the probability that the sum is less than 11 is 11 over 12, or 1 minus the probability that it's greater than or equal to 11. Other Any questions? Okay, so I just have these three examples just to demonstrate how you can use the complement. As I said, you don't have to use it. The places where you would use the complement is whenever you're asked for an at least or at most or less than, those kind of things. Those are good ones to use the complement. If I wanted to know how many was like added up to exactly 5, that's not a place where you'd want to do the complement, because if it's exactly 5, then the opposite would be that it's less than 5 and that it's greater than 5, so you've got 2 other things to add up. You can do it that way, but it is harder. And actually, I go back. This one right here, where we're looking at the probability of getting at least 2 heads. Just another way that you can think about it, instead of the probability that it's less than or equal to 1, you can also think of it as 1 minus, and then the probability that you have 0 heads plus the probability that you have 1 head. So I bring this up because if it's asking for exactly something, and then the opposite of exactly might be multiple pieces, and so you would have to add those pieces up and then do 1 minus that total of those other pieces. And this actually is kind of similar to on the application assignment. There's the very last question that's asking about the emergency vehicles. And there is, a question about, whether there's one vehicle available or none of them are available, or, at least one, there is one available. So you are going to have to do the complement for that problem. And I'm not going to tell you which one you have to do the complement, but it helps to kind of look at what you're finding probabilities of and treat the 2 vehicles as they're separate vehicles. So, it'd be one with the sample space that you'd have to write. You've got these 2 separate vehicles. They're not being interchanged. They're treated as separate events, that there's not overlap there. So, are there questions about the application assignment that I can, answer? I've just kind of referenced the first or the last question. I think the other ones are pretty straightforward. I'm actually going to look at my key. Yeah, the other ones are definitely pretty straightforward. Number 4 is a tricky one. I do have a video that goes over a very similar example to number 4. So you're going to want to look at one of my probability example videos for that. And then, yeah, number 5 is the one where you are going to have to do a complement, because there is an at least in there. And so that would be treated like what we did here. The probability of at least would be the probability of it not happening at all, depending on like how many you're counting. Okay, so if you guys don't have any other questions, cool, then this was nice and short. I am going to have to reschedule next week's. I think I'm going to do it during the day. And this is only because I'm going to be out of town for Thanksgiving, the week of Thanksgiving, and spending the evenings with my family. So I'm trying to do all my lives during the day so I can actually spend evening with family. So I think I'm going to try to do it around lunchtime, around noon, so people who may be working can maybe take some time off to watch it. But just a heads up, and I'll put that in the announcement in week 6 so you know exactly when that will be. And hopefully technology will behave, because I won't have my normal technology. I'll be just using what I can travel with. So we'll see how that goes. So thank you guys for attending, and hopefully I will see you next week. And if not, I hope you guys have a great Thanksgiving. So take care. Bye.